welcome to lecture 3 in week 10. And so in this lecture, we are going to look at what are called non-parametric filters, right? So far, we have been looking at Gaussian filters for state estimation, right? And the Gaussian filters essentially assume that your belief distribution is of a specific functional form, right? So in this case, it was we assume that it was a multivariate Gaussian, and it is described by a fixed set of parameters, in which this case, which was like mu and sigma, right? So even though we looked at a couple of variations of this, the fundamental underlying assumption is that there is a specific functional form, right, that describes the belief distribution, right, and that is given by a fixed set of parameters. So these are called parametric filters. Right? So now what we are going to look at are what are called non-parametric filters, and there are many non-parametric filters. We'll look at a specific one, right? So the idea behind parametric filters is that the idea behind non-parametric filters is that they do not assume a fixed functional form. They can look at arbitrary distributions. You can see here. So this is an arbitrary distribution. Doesn't look like a simple Gaussian, right? And so the idea behind non-parametric filters is that the complexity of the function that we want to represent, right, the density, the belief distribution that we want to represent, the complexity could vary to fit the distribution. So it's not like it's a fixed complexity function like the Gaussian distribution, right? It's not of a fixed functional form, but the function could vary. And typically, depending on the kind of samples that we draw from the distribution, we kind of increase or decrease the number of parameters that we use for describing the function itself. So even though we call it non-parametric, doesn't mean there are no parameters. It just means that there is not a fixed set of parameters which we use for describing the function. Okay. So the advantage of this kind of non-parametric filters is that they allow us to look at complex and arbitrary, in some cases, arbitrary distributions, and we are not restricted to Gaussian distributions, right? So if you remember, the problem with Gaussian distributions was that there had to be one hypothesis which we thought was most likely, and we had a small amount of noise around that hypothesis, right? So we could not look at hypotheses that supported us having multiple modes, right? So it had to be a unimodal belief state, and so the non-parametric filters allow us to get around that, right? So what we are going to look at in this lecture is a specific non-parametric filter called the particle filter, right? So in the particle filter, instead of representing the belief distribution as a function, I'm going to assume that the distribution itself is represented by a set of samples that are drawn from the distribution. So the curve f describes the distribution that I'm trying to represent, and the way I represent the distribution is by just storing a set of samples that were drawn from the distribution. Notice that this distribution is defined on one dimension, right? So there's just this x-axis is the dimension. The y-axis is actually the density for the values of the x, right? So for each value of x, the y-axis represents the particular density for that distribution. Right. So essentially, what I'm doing here is I'm sampling according to this distribution represented by f, and therefore you can see that wherever the density is high, right, I get a lot of samples, right? Wherever the density is high, I get a lot of samples, and wherever the density is low, I get fewer samples, right? And you can say intermediate densities, I have intermediate number of samples. So basically, instead of trying to represent this whole thing as a functional form, what I do is I just represent a set of points x in this case, right? I just store a set of points x, which in an indirect way represent the distribution. That makes sense? So in the case of a particle filter, I store a set of samples drawn according to the distribution, as opposed to storing, like, say, something like mu and sigma of the distribution, right? So instead of storing like a set of parameters for the distribution, I'm going to store a set of samples that were drawn from that distribution, and that will be the representation I have for my belief distribution, right? So so I'm going to make sure that we are specializing this discussion to beliefs, but the notion of particle filters can be used in a variety of other settings as well, right? Okay, so moving on. So in the particle filter, like I said, you take a set of samples, and these samples are called particles, right? So these samples are called particles. So the samples are called particles, and we denote them by x1 to xn, right? So this is basically a set of m particles, right, capital M particles, and each particle is, in some sense, you can think of as a hypothesis as to what the true world state may be at time t, right? It's just a guess, if you will, of what we think is the true world state at time t, and the way we generate these particles is by sampling from this distribution. So a particle at time t is sampled from the distribution which is probability of xt given z1 to t and u1 to t, right, which is basically all the observations I have seen from the beginning of time until time t, and all the actions I have performed beginning of time until time t, right. So basically, what is this? This expression is our belief state, right. So where do I believe that I am at time t, right. So this is essentially what our belief state is, and so the set of particles, right, are sampled from our belief state at time t, right. Now as m tends to infinity, m meaning the number of samples that I draw or the number of particles that I maintain, then this set of particles becomes a very good approximation of the underlying density, right. So the denser a subregion of the state space as populated by the samples, the denser the population of samples, the more likely is it that the true states falls into that region. So it becomes more of a proper representation of the underlying belief distribution, right. So the particle filter essentially represents the belief as a set of samples drawn from the belief distribution. So we don't actually explicitly represent the belief distribution as a functional form here, okay. Now, as with the earlier versions of the Bayes filter algorithm, so here is a version of the particle filter algorithm, right, and again we update the belief of xt recursively from belief at xt minus 1, right, and as before the particle filter algorithm takes as input the current action ut, the current measurement or the current observation zt, and our representation of bell xt minus 1, right. If you remember, initially in the Bayes filter algorithm, bell xt minus 1 was just supplied as it is, and in the Gaussian filters, bell xt minus 1 was supplied by mu t minus 1 and sigma t minus 1, right. In this case, bell t minus 1 is supplied by the set of particles xt minus 1, right. If you remember, that's what we said, right. So the distribution at any point of time is represented by the set of particles xt, right. So we start off with xt minus 1 as the set of particles that represent belief xt minus 1. So notice that, so what do I mean by the particles representing the belief? That means that these particles xt minus 1, there will be m such particles. So these m particles were obtained by somehow sampling from the belief distribution at time t minus 1, okay. Now I start off by initializing both my xt bar and xt, which are two sets of particles, and as you can guess, xt bar is going to represent bell bar of xt, right, or so the bell bar at time t, and xt is going to represent bell at time t, right, bell xt, right. So xt bar, which is a script xt bar, is going to represent bell bar of xt, and script xt is going to represent bell of xt. So that's what we're going to do, okay. So I'll just run through the steps, and then later in the next few slides you'll see how this implements the actual belief update, right. So what I do is, initially, so the lines 3 to 7, right. So lines 3 to 7 are running through each of my particles once. So my particle here is a sample, right. So each of my particles it's going to run through once, okay. So what it does, in line 4, right. So what is happening in line 4 is that, I take my previous particle and take one sample, right, which is the mth sample. I am taking the previous particle from my belief xt minus 1, right, and then apply the action ut, which I know. I apply the action ut, and I look at the distribution of the resulting state, right? I'm looking at the distribution of xt, and I'm just going to sample an xtm from this distribution. Right? Basically, I'm going to perturb this particle by the action. I'm going to move it forward, assuming that this is the actual state at time t minus 1. Right? I'm going to make a prediction as to what would be the state at time t, and I'm going to sample from that. Right? So, for every particle that I was using to represent xt minus 1, I'm going to sample one particle now to get me xt. Yeah, get the new xt. Okay. Now, this is a little tricky part here. So, what I am doing now at step 5, right? So, what I am doing at step 5 is essentially trying to account for the observation probabilities or the measurement probabilities. We know that zt was the actual measurement that we made, right? And I am assuming that xtm is the real state, right? So, I am looking at, okay, hey, if xtm was really the correct state, what is the probability that I would have made this observation, right? I am going to assign that as what is called as a weight or the importance weight for the sample xtm, right? So, I have wtm, which is the importance weight for the sample xtm, right? And then I have, I'm just adding to the bell bar representation, right? Bell bar xt representation, the sample xtm, right? So, the actual particle as well as the weight, right? So, I'm going to add the particle and the weight to the bell xt minus, or rather xt bar. Okay, it's not quite bell bar. It's actually something. So, the xtm incorporates the movement, right? xtm incorporates the movement, and the wtm actually incorporates the observation. So, the xt bar is not quite a representation of bell bar because it already incorporates the effect of the observation through the weights, right? So, in fact, I could just stop here, right? I could just stop here and say that, hey, look, now I started off with a set of particles which were xt minus 1. I had 1 to m particles. Now I have a new set of particles, right, xtm, and a set of weights that tells me, right, how likely is that the true state to be that particle. Does that make sense? This probability tells me how likely is it that xtm, if xtm was the true state, would have given rise to the observation zt, right? And now I have this weight that tells me, okay, how likely is it that this is the real state given that you have observed st. So, it's in a way I can still reconstruct my belief, right? I can approximately reconstruct my belief using these weights and these particles. And then what is going to happen is that since these particles are now going to continue, suppose I come to a point where a particle has a very low weight, right? Because it says, hey, look, this is very unlikely that this particle is something that would have given rise to this observation, right? Or that's a small probability event of, big noise, right? So, I'm trying to move forward 1 meter, but suddenly I move forward 2 meters. I mean, it could very well happen that somebody pushed the robot or something so that it moved forward 2 meters, but it could be a very, very low probability event, but then let us say that is the sample I draw. Right now, I've gone forward 2 meters, but the robot has really not gone forward 2 meters, it's gone forward only 1 meter. And then I make a measurement, I'm going to say, this measurement is quite unlikely, right? But then what is going to happen? I'm going to have a location that says the robot is 1 meter away from where it really is, right, with a very low weight. But then when I go back and try to do a resampling of this, when I make the next action, I will still keep pushing this particle forward. Right? And I'm going to give lower and lower and lower weight to it till it becomes vanishingly zero. So, what will happen is, because there is so much noise in the system, right, many of the particles' weight will go to 0. Right? And so, I'll be carrying around a lot of particles whose weight is 0, and it's not a great filter then, right? It's not a great representation of my belief. Right? So, if I have a lot of my particles have a weight 0, then I'm basically using only 1 or 2 samples to represent my distribution, and I could be very wrong in that. Right? So, we'll see that in a minute when we go to the actual illustration of this algorithm. Right? So, how do I overcome this, right? So I know I told you that already my xt bar has enough information that incorporates the observations, but the set of particles are not really great. So what I do is something called resampling. So this phase, right, lines 8 to 11 of the algorithm, I do what is called resampling of the particles, right? I have the same, I have m particles now, each having some weight, right? Now what I will do is I will resample m particles, capital M particles again, right? So it's a new set of particles that I am drawing, right? But the probability that I will draw one of the earlier samples, right? So remember that I am going to draw samples here with replacement from xt bar, right? So what I am doing in line 9 is drawing samples with replacement from xt bar. So people, all of you are familiar with sampling with replacement, right? So we are going to do sampling with replacement from xt bar. So what we do there is, okay, we'll pick a number I with a probability that is proportional to WTI. So what is WTI? It is the weight of the ith particle in my set xt bar, right? So I've computed m weights. So this WTI is the weight of the ith particle in my xt bar, right? So I'm going to sample an I proportional with probability proportional to WTI. Basically that means that I'm going to take each WTI divided by the sum of all the W's, right, and that gives me the probability that I will sample I, okay. Now once I have drawn a sample, I'm going to add the corresponding particle, right, the one that is here xti, I'm going to add it to xt, script xt, right. So I'm going to do that m times because m is the size of the particles that I'm maintaining. So I'll draw m such particles like this. Notice that these particles I'm drawing are exactly the same set of particles here, just that some particles might be drawn more than once and a few particles could just be left out in this new set m. Why could particles be left out in the new set m? Because they have low probability, right? And particles could be repeated in the new set m because the probability of the probability mass in that particular state in the belief state is very high, right? And then I do this for m times so that I get a new set of samples m, and then I return xt. So remember, so the last thing that return is bell xt. So this is basically bell xt, okay. So this is not quite neatly broken down into the first step where I compute bell bar and the second phase where I compute bell, right? So the first phase here is where I actually do my prediction as well as accounting for my observation, right? My prediction and the correction computation is already done in the first loop, right? So that is my prediction computation and that is my correction computation. I'm already done that in the first loop, and what I'm doing here in the second loop is essentially resampling the particles so that I actually get a more appropriate representation for bell, okay. So as we said earlier, so the set of particles that I get from the last step, right? So is essentially my representation for bell of xt, and so the one that I get in step 4 is kind of, so step 4 is that, right? So the set of particles is kind of my representation for bell bar, right? So that's not yet yet incorporated my observation values. So that's, it's a representation for bell bar, and what I finally get from line 9 is my final representation for the belief of xt. So let's look at now let's look at just, I'll skip this slide, I'll come back to this. Let's go over this slide itself, right? So so like we said now, right, lines 8 to 11 implement what is known as the resampling or the importance resampling process, right? And as we said, the algorithm draws m particles with replacement from the set xt bar, right? Remember that xt bar is really not bell bar t, right? So actually the original set of particles that we sampled in line 4 is our bell bar representation, not now, right? Now what we do is essentially doing something like this, right? So our bell of xt is now sampled, is now kind of equal to the observation probability, the probability of zt given xtm times bell bar xt. So each particle that I am sampling here, right, is going to be sorry. So we have to edit the last part when I start talking about resampling. Okay. So I'm going to redo the whole thing for this slide. Okay. So like we looked at when we were discussing the algorithm, lines 8 to 11 implement what is called resampling, and sometimes it's called importance resampling. And again, I'm going to draw m particles with replacement, right, from the set xt bar. Remember, xt bar is not really the set of particles representing bell bar, right. So the bell bar is essentially whatever we computed in line 4 gives you bell bar, and xt bar is the particles with the weights, right. And like we mentioned, this is already encoding your bell xt in some way, but the particles are not the right set of particles. Therefore, we get a better set of particles by sampling with replacement, right. And so before I sample with replacement, they were distributed, the particles were distributed according to bell bar xt. So that's what we said, right. So the xt's were a representation of bell bar already after line 4, but after the resampling, they are distributed according to bell of xt, more or less, right. So that's basically the idea here. So so let's look at how this is going to work, right. Here is a simple belief representation. You can see that already this is something that a simple Gaussian filter can't do, right. So we are basically having a bimodal distribution. So the state x here is just a single line. Yeah, it could be anywhere on this x-axis. The robot could be anywhere on the x-axis, right. And I'm going to assume that there are these two peaks, right. I'm not sure whether the robot is here or whether the robot is here. Of course, I'm going to have some baseline probability that it could be anywhere on the line because of the noise, but most of my probability mass is now concentrated around these two modes, right. And the way I would do my representation now here would be a lot of particles will be present here, and another set of particles will be present here, and there will be very few particles elsewhere, right. So maybe there are one or two in other places, but most of the particles will be present in these two modes, right. So this will be my representation of this kind of a belief state using a particle filter, right. Now let's assume that I do the action move right. Right, I do the action move right. So what should happen? So what I'm going to do is I'll pick one particle, right. So this is what we do, right. So I pick one particle from the set of particles that represent my belief, right. This is my probability of xt given ut comma xt minus 1 m, right. So that's basically the line that we are trying to look at here. Just let me go back so that you can see what we are talking about, right. So what I am doing here is step 4, right. So I am going to look at the probability of xt given that I am applying ut to xt minus 1 m, right. Some particle, the mth particle at time t minus 1, I am going to pick that, I am going to apply action ut, and I am going to sample xt. So that's basically what we have done here, right. So I have taken a particle here. So you can call this, you can think of this as xt minus 1 m, right, and I have applied ut, which is just this action go right. I have applied ut here, and then I have sampled from the resulting distribution. So assuming that it ends up here, so this will be this red dot will be my new xt, right. So this is xt minus 1 m, this is xtm, okay. So that's basically the step, right. So for every particle here, so I'll pick that, I'll apply the transition, whatever is the action, and I'll sample from the resulting distribution, and I'll get a state, okay. Great. And now moving on. So now what is the next thing I have to do? Once I have done that, basically I end up with this as my belief distribution. You can see that, right. So from these two being my modes, right, now I have become, these two have become my modes. I have basically moved, right. So basically what does this mean? The set of particles that were here, right, have moved here, right. The set of particles that were there have moved here, and the set of particles that were here have moved here. That makes sense? Okay. And you can see that it is flattened out a little bit. It is not as peaked as it was here. It has flattened out a little bit. Why is that? Because there is some noise in the movement, right. So when I try to move one particle from here forward, right, it doesn't always move the same distance forward, right. There will be some kind of a region of uncertainty around the end, right? So it might end up here, it might end up a little bit earlier, or it might end up a little bit later. So the motion need not be deterministic, and there will be some kind of a smearing out of the particles, and that's essentially what you see here, and why this looks a little bit more flat. Okay. Next, what I have to do is account for the, right, I have to account for the observations, right? So now this is what my observations tell me. What does my observation tell me here? So okay, so whatever the observation I have seeing now, right? So maybe I'm seeing like a patch of red on the wall, or I'm seeing a door on the wall and things like that. So that door or patch of red could only occur in these two places. There is a door here in the world, and there is another door here, right? There are two doors here. There's a door here, and there's another door here. And now, even though I have moved to the right, okay, I have moved to the right, and I actually still see a door. Let us say my observation says that, hey, there is a door in front of you. Okay. Now we know from the way the observation works that the door can only be seen in one of these two places. We know that the door can be seen only in one of these two places. So what does that mean, right? The robot has to be either here, right in front of this door, or it has to be in front of this door. But we started off with the belief that had the robot in front of one of the two doors, and now I have moved right, correct? And again I see a door, right? So I know from my observation probabilities that it has to be one of these two places, but I know from my motion model it has to be one of these two places likely. Therefore, I'm most probably here, right? I'm most probably here. So how does that work in this particular case, right? So now let's pick a few particles now, right? I'm going to tell you how this whole importance resampling part works. Okay. Now we already saw how we projected one particle and got this. So we got this particle here, and how we projected. Now we could have projected this forward, and let's say we got another particle here. I'm just picking 3 particles as samples, right? And then this particle could have come from either the motion model telling me that a particle hasn't moved at all. There's some probability of xt being the same as xt minus 1. Maybe that's a chance of a failure of the action, or it could be that there were some stray particles here or there to accommodate for the background noise, and one of those particles kind of happened to be here, right? Just whatever is the reason, I'm going to pick these 3 particles as samples to tell you how the importance resampling is going to work, right? So when I start off, when I do the prediction update, right, when I'm actually moving these particles forward based on the action, all of these start out with an equal weight, right? So all of these would have notionally equal weight. I have not assigned weights yet, right? But now I'm going to assign weights, right? So how are my weights going to be? They're going to be looking at the probability. I'm going to add the probability that the observation happens here. So literally, so the weights will now, there will be a lot of weight for this guy, because okay, I have my, so this is my posterior, right? I've updated this. So this is my prediction bell bar, right? And this is my it's going to be the overall weight assigned to this particle. So these now sizes have become proportional to the weight, and these you can see that have actually gone down from their default value. These weights have become very, very small. Now what I'm going to do is I'm going to resample these particles according to these weights, right? When I resample the particles according to these weights, then what will happen is more and more particles will end up in this region as opposed to the other regions, and I can see that even though this was my bell bar update, right, after I do the reweighting, right, after I assign the weights and I do the resampling, this becomes my bell, right? So this was my original bell. This is bell of xt minus 1. This is bell of xt, and this is bell bar of xt. Okay, makes sense? So this is exactly how the particle filter will operate. So I'll have a set of particles to begin with, right? I'll have a set of particles to begin with. I'll pick each particle from here. I'll apply my action, right? And I'll sample from the resulting location, right? So I'll have a distribution over where this particle could end up. So I'm going to sample from that. So I'm going to basically take this set of particles and I'm going to move them, and so I'm going to get something like this. So there will be a slightly spread out distribution that looks like that, and then I'm going to accommodate my observation probabilities, right? I'm going to accommodate the observation probabilities. The observation here, as you know, was that I saw a door. Therefore, I'm going to accommodate that, and wherever the particles correspond to the motion being reliable and the observation matching what you see, right? Those are going to get a high weights, right? Now I'm going to resample these particles, right? These particles would have now moved out over here. I'm going to resample them according to the weights, right? So probability proportional to the weights, and I'll end up with something that looks like this, right? There will be a lot of particles in this space, right? So many of these particles will end up coming here, and fewer particles would go here, right? Basically, I'll be resampling the same particle multiple times, because as you can see that, right, if my density here is going to be much higher than what I had as densities here, so more fraction of my m particles, right, my capital M particles, a larger fraction of those should end up in this region, right? A larger fraction of those particles should end up in this region. So how is that going to work out? So a lot of particles that are here will receive a small weight, and when I resample, many of them will not even get sampled, right? Remember, I'm sampling with replacement. So if these particles have a small weight, they will not get sampled. But the particles that are here, right, and because they have a large weight now, all the particles here that have a large weight will get sampled again and again. Again, remember, I'm sampling with replacement, right? Even if I sample a high weight particle once, it goes back into the pool, so I might actually sample it again, right? So many of the particles that correspond to this part of the state will keep getting sampled again and again. So I'll be repeating those, right? So I'm basically going to make my the particles, right, set of particles get concentrated around this region. Maybe there will be one or two occasional particles that are spread out, but most of my particles are going to be here. So the next time I'm going to do a forward or a backward action or whatever motion here, right, that activity is going to basically be applied to this part of the state space and less likely to the other parts of the state space. So mostly the particles will get concentrated in one region of the state space, right? So I hope that makes sense. So what I'm going to do now is just go back and look at the algorithm once more, so that it's now people can see it more clearly. Okay. So what we do here, we start off with a set of particles that represent belief at time t minus 1. I have my action at time t, and I have my observation at time t, right? We saw all of this. The action was to go right, observation was see a door, right? And now for every particle that I have in x script x t minus 1, I'm going to take each particle one at a time. That's, I'm taking the particle, I'm applying action ut, right? I'm going to apply action ut, and then pick a new particle xtm, right? So that's a particle corresponding to t minus 1, and this particle essentially, you can think of it like, hey, I'm moving my state from xt minus 1 to xt, right, because I did action ut. So that's basically it, right? So at this point, at step 4, we saw that the second belief that we had, right, so the bell bar is formed by doing this. The next thing I do is assign weights depending on how likely it is that I'm going to see an observation, given that this is the particle that I have drawn, right? And it turns out that so the places where we can see a door is the one that we are likely to pick, and so the weights for those are very high, right? And now, right, and then I'm going to assign I'm going to add the weights to my particle and create xt bar, and I'm going to resample from that, right? And when I resample from that, I'm more likely to sample in particles from regions which correspond both to the motion prediction as well as to the observation probabilities, and that's essentially what you saw here, right? So this is what happens when I do the resampling, and so that's basically what the particle filter does. Okay. So particle filters are great, but there are some challenges with using particle filters. So the first challenge is we use a finite number of particles, right? So you know that we said that when m tends to infinity, right, and capital M tends to infinity, the particle filter approximates the true distribution, right? But for a finite number of particles, there are all kinds of problems that come in, and we typically say that the representation is biased, right, because of the small number of particles that you are using. And if there is a more nuanced, more complex distribution, you might not have enough particles to represent the whole region, right? But then what we typically find in practice for most applications that we are interested in the robotics domain is, as long as m is reasonably large, say even 100, right, or maybe in the hundreds, if you will, right, this bias effect is negligible except in very, very rare cases, and therefore for all practical purposes you can still use the particle filter, but you have to use a large number of particles. You can't just say that I'm going to use 3 particles, 4 particles. You'll have to use a large number of particles to make sure that you don't get into the biases associated with the finite number of particles. Okay. So the second problem is there is a high variance, right, that comes in when you're using a particle filter because of the randomness that we are having in the resampling phase, right? So what happens is, if you remember what we saw here in this particular case, right, a lot of these samples, right, that were retained in your Bell representation were essentially the same sample being repeated, right? So, and this is something that will always happen, right? So, I suppose I had like 10 samples here and I had 10 samples here. When I do the resampling, right, I'm going to get say 18 samples here and 2 samples here, right, and just to keep the numbers small, right. So I had 10 here and 10 here. Now I do the resampling, I'm going to get 18 here and I'm going to get 2 here. So the 2 is not a problem, but if the 18 is going to have a lot of repeated copies of the same 10, right. So basically what is happening is I'm kind of reducing the variety in the particles. Okay, now that is fine. You'll think that reducing the variety in the particles will reduce the variance. It does, right? But that is for a specific run of the particle filter, right? If I give you the same sequence of observations, right, and same sequence of actions and observations and ask you to rerun the particle filter, just because there is a randomness here in which particles I choose to resample, right, I might end up with a different set of particles being repeated. Again, the variance could be low for that particular run, but across runs, right, which particles I retain and which particles I use for continuing to update my thing, right, could be very different, because I'm going to concentrate on a small number which are repeated, right. I'm going to concentrate on a small number of particles that are repeated. So this could lead to a huge variance in the estimate, right. So one way of getting around it is to say that, hey, I'm getting this only because I'm resampling so often, right. So every time I resample, I kind of reduce the variety in the particles, right. So why don't I resample, maybe at a lesser frequency, right. Right. So I can reduce the rate of resampling. Instead of resampling after every movement, maybe I'll resample after every 10 movements or every 20 movements or every 30 actions, right, instead of resampling after every action, right. So that's one way of doing it. And then there are other things called the low variance samplers for the particle filter, which we could use, and I'm not getting into that. I mean, it's discussed in the book if you're interested in looking at it, right. But then when I'm going to reduce the rate of resampling, I have to be very wary of some things, right. So we already saw that if we resample too often, we lose the variety in the samples. But on the other hand, if we resample too infrequently, right, if I say I'm going to resample every 100 actions or every 200 actions or something like that, what will happen is the problem that I pointed out earlier, right. I remember I said what happens if you don't do resampling, right. I can still reconstruct my belief just by using the particles I get for my bell bar and the weights, right. But what will happen is, as I keep doing these updates again and again and again, the particles are more likely to move into low probability configurations, and eventually the probabilities go to 0 of the particle being there, and that is going to create a problem because my set of particles will become not very representative. I will only have a very small set of particles, not the m that I thought I have, right? So, so if I resample too infrequently, we'll have a majority of the particles in low probability configurations, right? So we have to figure out what is the right rate of resampling so that we can maintain this, and it comes from, it's a lot of factors that go into it. It depends on the complexity of the motion model, how noisy your sensors are, how noisy your actuators are, right? And so it typically takes you a few iterations before you can get this this whole thing correct, right? And it becomes easier with more experience using these, right? And particle filters again are very popularly used in many of these state estimation problems, right? And there are a couple of other challenges, right? So one problem is that so the bell bar and the bell distributions, right, can become very different when when we have sensors and actuators that have different levels of noise, right? Here is an extreme example, right? Consider the case when the sensors are almost deterministic, right, and the motion has some noise, right? So now what happens is I move forward, right? I move forward, and then my motion model is going to smear my particles out over a range, right? But let us say that my sensor is very accurate. It can tell me exactly what the x and y or the x coordinate is for the robot. Now, since my motion model is noisy and it has smeared out the particles, most of the particles are going to have a weight of 0 because they are not at the right xy coordinates, right? In fact, given the way this whole thing is going to operate, almost all my particles will have a weight of 0 because maybe one or two of them will actually end up at the exact right coordinates. Most of the others would be slightly off, and since my sensor is deterministic and gives me the exact x coordinate, right, all the others, the probability of z, which is a specific x coordinate given the location of the particle, would be 0, right? So what's going to happen is my weights, right, almost all fade away to 0, and now sampling with replacement is just not going to make any sense, right? Maybe there will be one or two particles or which will have a non-zero weight. I'll basically be repeating those particles again and again. Now this will be very different from what is the actual belief that I wanted to represent, okay? And in fact, what happens is maybe in one step you get that, but as you keep repeating this updates multiple times, you will have all your weights go to 0, in which case you will have no particles to resample, right? So one of the simple ways that people address this, typically it comes from having sensors that are too focused, right? So but you are not able to predict the motion correctly. So what people do is they assume that the sensors are noisier. Basically, you look at your probability of z given x and you add a little bit of noise to it. You don't use the actual probability of z given x. You add more noise to it than is actually there in the sensor, right? And this allows you to get around this. Is a very cheap and simple way of making sure this divergence problem doesn't happen, right? And the last challenge, I shouldn't say problem, last challenge in implementing particle filters is something called the particle deprivation problem, right, or the particle deprivation challenge, right? So typically, we have been talking about one dimensions, other things because it's easy to draw, but typically you're operating in a very high dimensional space, right? So a lot of different state variables that you have to take care of while representing the robot, right? And any small finite set of particles, even if I'm talking about 100, 200 or something like that, it will always be sparse in a high dimensional space, right? So when I'm randomly resampling things, right, especially when I'm doing my random resampling, right, so I could very easily come to a point where particles that are close to the true state vanish, right? So instead of being at the exact correct state, right, instead of being close to the true state, I might actually sample things that are slightly farther away. And given the space is high dimension, right, so everything is sparse, right? There will be only a few particles to begin with that were very close to the true state, and now they will vanish because of the random resampling, right? And I could start sampling slightly farther away from the true state, but then once I start projecting those particles into the future, right, they'll move farther and farther away from where the actual state of the robot is, and I might come to a point where I might not have any particles close to the true state for me to make any reasonable belief updates, right? I might actually be completely deluded into thinking I'm somewhere else, right? So one way to address this, right, is to not resample m particles every time, resample something less than m, and then add a small number of new particles, right, sampled uniformly over the space, and just randomly, reset some of the particles instead of just looking at where I was projecting it and going, just randomly reset the particles to somewhere over the space and then continue that. So your importance resampling, instead of sampling m states, m particles, will sample a number m minus k, where k is the number of particles you add to refresh the particle set, right? And you don't have to do this at every time step. If you do this every time step, then you are actually losing the whole effect of the particle filter, right? You do this, say, every few time steps, maybe every 10 time steps or every 100 time steps, or you could do something more cleverer. You could look at the variance of the particles. If you find that the particles are all, kind of clustering around one state, right? Then you could say, hey, I'm going to do a resampling, right? I'm going to do this refresh of the particles. So you could say, okay, the variance of the particle space is getting low, I'm going to just stop and resample, or add a new set of particles. Not resample, it's refresh. I'm going to just refresh the particles, and so I'm going to take a k new particles and then add them randomly over the space, and then I'll start updating. Hopefully it'll cover up for any problems that could be there. Okay, so particle filters are very powerful. They allow us to model arbitrary distributions. They're simple to implement, right? And in many cases, people have very efficient implementations of particle filters, so that you can do this at runtime, so the robot movement is not impeded by all the particle computations that you have to do. And the other thing is, I didn't say anything about what the motion model and what the observation model should be. I mean, there could be anything. I don't have to assume any specific form for it, as long as it is easy to compute, right? So that I can plug that into my lines 4 and 5 of my algorithm, and I can do this, right? As long as it's in some form that's easier for me to sample from, right? And there are some caveats. There are some things that you have to be careful about, but given advantages that you get of using particle filters, so it makes sense to look at these challenges and make sure that you're addressing them. And like I said, there are easy ways to address these challenges, and there are more robust ways to do this as well. And so we just go ahead and use particle filters. Okay, I'll stop here.